Thank you. All right, so many of you have seen many of these slides before, some many times, but we're going to do it anyway for those who are new and also for a refresher. So what are we doing as a mission? And this slide, I think, sort of brings it all the way back. We are trying to unify two fields of heliophysics. Traditionally, on the left, we have a LASCO sequence that represents the sort of remote sensing aspect of solar physics. On the right, we have space physics typified by what I used to call a confusogram, but I now know better. That's a trace of many characteristics of the plasma as it washes over a spacecraft. And we're in an exciting time. Right now, we have a different mission, which is represented here. I think Noor is in the room. For Parker Solar Probe is flying inward and bringing sampling into solar physics. This brings to bear essentially an electron microscope that allows us to see the local physics on very small scales within the corona, as well as just get the ground truth for many processes. Punch goes the other way. We are looking at the anatomy, if you will, of the large-scale structure. We're bringing large and cross-scale context outward from the sun into the solar wind by imaging the solar wind, much as is a counterpart to Solar Probe, which is bringing sampling inward to the corona. So together, I think we're going to see a complete change in the way we view this system. We will be able to study as well as just conceive the heliosphere as a unified part of the corona as a full system. So you've all seen this slide before. This sort of summarizes what we are as a mission, right? We're trying to understand how the corona gives rise to the heliosphere, and by extension, how stars give rise to their heliospheres. We're doing it with direct continuous imaging in 3 dimensions. And we're doing that with polarized light. I'm not going to talk about the physics of that, but we do have another talk tomorrow by Nathaniel Laurent, who's here, probably our youngest speaker, who will talk about having traced CME location in a simulated corona. So that'll be tomorrow. And of course, we have 4 synchronous satellites. You walk past models of 2 of them. They're synchronous in the sense that we operate them as a single virtual instrument. So 4 spacecraft, 1 instrument. We're going to 650-kilometer sun-synchronous orbit, hopefully this weekend, for a 2-year nominal mission. But the orbit won't decay for at least 2 decades. So we hope to operate for a long time. These are our science objectives. I'm not going to run through all of the names of all of them because you mostly are familiar with them. We have 6 topics, which are organized as 2 major science objectives. And those can be summarized as understanding the ambient wind and understanding the transient structures in that wind, which give rise to space weather. This is a movie that we made a long time ago with stereo. I noticed Russ Howard is in the room, PI for SECI that made this sequence. This is polar coordinates, but we're showing that, yes, solar events, things that take place in the low corona, do affect the Earth directly. This is tracing a storm, CME. It's a room full of scientists. I shouldn't say storm. Tracing a CME out from the sun across, sweeping over Venus and impacting the WIND spacecraft in front of the Earth, driving that gauge. So this is our field of view. And the idea is to make a seamless field, and the SOC team are working diligently on that and have done amazing things to make that happen. Because even though we advertise this as seamless, there are lots of seams because we have 4 separate cameras. And so getting rid of those has been a real effort, but we're ready for it. I want to point out one of the things we're doing is really good photometry, and I mean really good photometry. We are all used to what LASCO looks like, and punch data will go as far in as the LASCO C3 field, but they will look quite different. And so the best demonstration that we have today of what that will look like is the SEACOR data that recently started being streamed. This is the first press release movie. I just happened to have it. But the historians often say that quantity has a quality all its own. If you have a 1,000,000-man army, that's got a quality that's different from a 100,000-person army. And in this case, signal to noise has a resolution all its own. So the corona will look different in Punch than you're used to, just because the images will be lower noise and therefore crisper, even though the field of view is one that you're familiar with. There's that movie again. These are our instruments mounted on observatories. The one on the left is NIFI, which was made by NRL. We have Robin Colanino here in the room. On the right, we have WIFI, which was made at Southwest, led by Glenn Laurent, who's also in the room. Glenn Laurent, excuse me. I've been trying to do that for years, so forgive me. Anyway, three of those, we have models of them one-to-one out front, so you can familiarize yourself with just the visceral scale of how small these things are. This is what our data look like. You've seen the older version of this movie for a long time, but we are here rendering an actual set of data that's been run through the SOC pipeline after being forward modeled. So Elena Provnikova, who's I believe in the room, right there, hi, simulated an entire solar system, thank you, and a CME, and Sarah Gibson forward modeled it, and the SOC team went after it to try and simulate what we would see after all of our background subtraction. So there it is. To make that happen, we had to design the instruments right, but we also had to do a lot of work in the SOC. That's a 90-degree field of view for those who aren't familiar, which is huge. We're into the baby pictures section. Those are the 4 instruments last week, or the 4 spacecraft actually, mounted side by side in the clean room in Astrotech. They have since been integrated. They're tested, they're working fine. These are some pictures of things like the solar array test there. In the upper left, you can see the underside of one of them. That's the side that normally faces the Earth. And that little tiny circle right in the middle, the large circle is the motorized light band, which separates the spacecraft and has springs in it to get us out to where we need to go. And that little tiny circle in the middle of it is a rocket engine, which we use for orbital trim. So that's a hydros engine. We don't carry fuel, we carry propellant in the form of water, and we electrolyze it to make fuel and then burn that periodically. So we don't keep much fuel around for safety. We make it on demand. And then down below is contamination testing the wiring on one of the solar panels. These are images of us being mated to the ESPA ring. We are fully mated and stacked with Spherix. The images haven't been released, so I can't show them to you yet, but they're in process. So hopefully by the end of this meeting, we'll be able to show you. But we are mated to the ESPA. We're ready to go. It's been a long journey. You've been watching a little red arrow crawl across this plot for years now, some of you. This plot doesn't even go as far to the left as we started. We started in 2015. So phase A picked up in 16, earlier in 16 than this chart shows. We had COVID in the middle. We had a change in launch vehicle. We had various mishaps involving radios and things happen. It's been a long and twisty road to get here, but here we are. We're on a green line, not a red line, just before launch, just imminently. So give yourselves a round of applause for sticking it out. It's really... All right, so ground systems are really important. I often talk about it. I'm not going to go on at length about the amazing things that have happened in the SOC. I'll leave that to the SOC team. But we have everything ready. Data flows through the ground data network all the way to the right to the Mission Operations Center, which is ready to go. They've been drilling for weeks. To the Science Operations Center, which will get it to you via the SDAC. We are returning to the original purpose of the SDAC, which is to be a central repository, not dependent on any one mission team, to distribute data. And there are lots of reasons for that, but none more clear or in your face than what happened to the SDO JSOC, right? Data distribution rises above any one institute, and Stanford is a fine place and they do an excellent job. However, we wanted to make sure that our data were not subject to whatever facilities we happen to provide at Southwest. So we're distributing everything through NASA. You can get it through the VSO, and there'll be a tutorial session a little later on in the day that Chris Lauder will run after Marcus tells you about the sock. I'm not going to talk very long about the mock, but I want to show you a picture of it. This is it. We operate Punch from Boulder. It's actually right across the hall from my office. Fancy that. But we have a full multi-mission operations center there that will speak directly to the ground data network over redundant internet lines. So we're good to go there. Jillian Redfern leads that, and the operators have indeed been working on procedures and drilling for weeks. So they're in tip-top shape. The sock is ready. We have the most sophisticated sock of any explorer, and hats off to the sock team who've been diligent on working on this for years now, and push the state of the art in image analysis. We are doing things to images that no mission has done before. In particular, we solved the problem of coma in our images. Marcus Hughes has a paper out, Coma Off It, love the title, that describes a problem that dates back to 1611. The first reference we could find was in Latin, and it was by a pair of guys named Kepler and Galilei, who wrote about the problem of coma in their telescopes. So congratulations, and that allows us to merge the data seamlessly. So actually a round of applause for the SOC team. We include 30 days of constellation cross-calibration during commissioning. That is to say, we commission the spacecraft, then we commission the instruments, then we commission the constellation as a unit. And that's really important because it means that when we start phase E, we expect to be able to flow data right away. And we do publish all of our data to everyone immediately. So there is no proprietary period. You can get it on the VSO as soon as we have it ready. And the VSO indexes it. You're going to find out more about the SOC, I already mentioned that, and more about how to use the data. So stand by. All right, and we are the dream team. This is amazing. I'm so proud of our science team. We span continents, and folks have come here from halfway around the globe. Deepankar Banerjee came here from India and should be in the room. I don't see you there, right there. So, and if there is anyone who is not on our team institutionally who has done work in heliophysics, I consider that an oversight. So we really got the top groups in the nation to join. And furthermore, this meeting is open, so there are people who have not learned about Punch before. Welcome. We also have an associate investigator program that recognizes and encourages our scientists. I'll come back to that in a moment. I want to thank Sarah and our working group leads. We have 6 working group leads written in small print. That's Raphael Atier, Nikki Weil, Rohit Chibber, Anna Molyneux-Schenko, Kurt DeKoning, and Heather Elliott. And 2 of them are co-led. Raphael and Steve Cranmer are leading group, the Solar Wind Flow. Sorry. Oh, I'm sorry. And Barbara, excuse me, I'm getting it backwards. And working group 2 is Anna Molyneux-Schenko and Dave Webb. Good. So there's been a tremendous amount of organized, concerted activity. We organize these teams so that everybody's on at least 2 to make sure we don't get siloed. And we're ready to execute once the data show up. I want to talk about the AI program. I am wrapping up. We have 9 associate investigators. They're all here in the room. I'm not going to read them off because I'm short on time, but everyone's name is there. And I'd like to point out all of you will be co-Is starting in phase E. So this was a wonderful on-ramp to the team, and welcome aboard. I'm really thrilled that we can bring you on as full co-Is. So thank you. I want to mention STEAM. STEAM is an instrument that was built by undergraduate students, and it is a highly successful project in the sense that lots of students have gotten a real taste of space flight and experience. Over 50 students interacted with it. STEAM will be switched off because of a mishap that happened during thermal vac. but it has already accomplished its primary purpose, which was advancing education and training people up to become the project managers and engineers of tomorrow. So I'm pretty thrilled with it, even though you won't see STEAM mentioned in many of our science talks. We're not going to turn it on during the primary mission. We may try to turn it on later. This talk wouldn't be complete without Punch Outreach. The Punch Outreach program is best in class. It's built around the theme of ancient and modern sun watching. I'm sure you're all aware of it because we've been hammering so hard on it. We're building the next generation of heliophysicists and scientists by lighting up kids now and educators as well. We've seen lots of novel pedagogy and new aids to improve STEM engagement. They were working by tested, vetted, and optimized methods by iterating. And they've directly affected over 250,000 children already, in addition to side-on effects. So this is a tremendous accomplishment. And I want to thank Sherilyn Morrow, who's in the back of the room, and John Keller for leading that. And this was designed for as a regional program, but it's having national impact. So, well done. It's time to change the world. We're going to be getting data before you know it, less than 100 days from today. We're going to make the invisible solar wind visible. And the people in this room are going to get that out to the rest of humanity. So thank you. That's it. Go Punch.
Thank you, Craig. We're all really excited for this to move forward, and we're going to be open questions from Craig when we all gather in a few minutes. Yes, later. Questions later.
Craig, as much as I wanted to introduce some of the NASA community that's here.
And okay, so if you want to do that very quickly, you need to turn the mic on because the people, one of our AV will help you. Go ahead.
So we have Dr. Therese Morgan. There's so many new people, and she's our research director at NASA Geophysics Division. Next to her, her better half, but also Director of Science, Dr. Michael Hess. I'm just taking the opportunity to introduce some of the NASA members. We have David Chidi, without which this mission would have been ordered. Program executive at NASA. There is Nikki Weil, who is the project scientist at NASA Goddard Space Flight Center, but also very much a part of the science team. And I stand here being the Punch program scientist. Thank you.
Thank you, Lika. We really appreciate it. And this is, NASA is doing such a wonderful job with Punch. We can't wait. Okay. So the next speaker is going to be Robin Colanino, who is the instrument lead for the NIFI. And she's going to tell you all about that.
Hi, good morning. Yep. Okay, we're all ready to go. Hi, yeah, I'm gonna tell you about NIFI, similar to Craig's talk. If you've been here since the first Punch mission or the proposal, some of this is gonna look very familiar to you, but hopefully there's some new people in the room now. So NIFI will be providing the inner part of the integrated virtual observatory that will be the Punch field of view. Our requirement for the NIFI field of view is 6-hour sun to 30-hour sun. We're probably going to do better than that, but I don't want to make any promises until this thing launches. But we will be providing that center part of the field of view. We will be also rolling, which you can't, because our field of view is symmetric. You can't actually see in this movie as well. But and NIFI sits on its own spacecraft, and we will be providing images every 4 minutes. And to fit onto one of these small stats that is the Punch mission, we utilize the compact coronagraph design, which was developed for the GOES missions for this, and Craig already showed the beautiful SEACOR 1 data. So we hope that this is SEACOR's sister. So we hope it'll look just as good as that SEACOR data. So here's the instrument layout in a couple different views. At the top, you can see the exterior view. There's also the beautiful model outside in the lobby to see the exterior. Then the instrument itself, you can see in the side cutaway view, has three main components. The first is kind of the green area, which is the business end of it, where we do all the stray light rejection. Then in the center there, in the kind of teal, we have the lenses. That's what we call the telescope. And at the back, underneath the large purple radiator, we have the camera. So those are pretty much the three parts of the NIFI telescope. And here's that again, but in block diagram form. And at the bottom, we have the block diagram for the WIFI instrument. And because these instruments are really meant to be parallel by design, so that we can create that global virtual field of view. And so we also leveraged several common subsystems so that we have even more similarity between all four instruments as part of PUNCH. So we have here the stray light rejection part at the front, in front of our NIFI door. Both NIFI and WIFI have the same pin puller. And then we have the telescope optics after that. You can see the parallelization. We have our polarization wheel that's behind our optics, while WIFI has it in front. And then, of course, we have the same camera. So it's all meant to go together into that same field of view. And then we also have the same electrical interfaces that are being presented to the WIFI spacecraft. So we could have switched them around, but we didn't. So there they are where they are now. All right. And then again, going with that parallelization of polarization theme, we have parallelized observing plans. So in each one of the 8-minute orbital periods as we go around the Earth, WIFI and NIFI will be taking images at the same time for the same duration, so that we have both parallel. We can create these beautiful virtual fields of view with synchronized data. And we'll be summing images. You can see the little hash marks for NIFI, but it'll all end up being about the same. So, okay, so here's some beautiful hardware photos, what everybody comes to see, beautiful hardware photos. So the front half of the instrument is the stray light suppression assembly. So at the center, at the heart of the instrument, is the occulter, which you can see there. That is integrated into the front aperture, A0 aperture, which is serrated. And then we have the pylon at the bottom to hold the occulter in place. And then we have baffling interior to that stray light tube to reject any secondary, or reject like Earth light and any secondary bounces coming back from the heat rejection mirror. And then over here in the beautiful image, we have the calculated vignetting for the instrument. And you can see that with the lavender and white areas, we have a large area where there is no vignetting in the instrument, so that we have an area where we can do very good cross-calibration with WIFI. So our the NIFI optical lens comes next in after our entrance aperture, which we call A1. You can see the lens assembly there at the top, and then here we have a mosaic at the top here, showing where we measured the spatial resolution in our vacuum testing. So you can see the next to each one of those numbers is a little tiny white blob that you can't see, but if you would zoom in, you would see that those are actually Air Force test targets. So we measured the resolution for the instrument at all these locations, and we found an MTF of 0.419 at 93 arc seconds. So that means that we're expecting a spatial resolution better than 93 arc seconds, but we met the requirement and we stopped measuring. So as any good instrument should. But this, this is the optical layout, and so we're very, very good, lens design here. And so we should be getting a superior quality image. This is a picture of the heat rejection mirror, which is a very, very finely polished mirror. The heat rejection mirror lives kind of on the interface between the straight light assembly and the telescope. It has two purposes. As the name implies, it rejects heat from the sun back out of the instrument. It's actually an off-centered focal parabolic mirror. You can see the focal point here at the bottom with the green rays coming back. So it actually makes an image of the sun near the occulter and then rejects all of the light out of the front of the straight light tube. And so that gets the heat out, and it also gets the straight light out. So we don't have sunlight bouncing off the back of that straight light assembly and getting into our aperture here that's at the center of it. So, all right. Then just a little bit on the NIFI structure itself. You can see kind of a naked NIFI here in our aluminum structure. So the NIFI, you know, we had to design that to accommodate both the very the needs for the optical components, the tight alignments, and to make sure that all of those tight alignments stay where they should be on Friday when it launches. So we use design, and then it's attached to the spacecraft via 3 flexure mounting points on the spacecraft. And then we have the camera there with some thermal hardware attached at the top that is mounted kind of cantilevered on the back of that structure at the bottom. So then we have the NIFI door, which is a single one-time open door. And this is providing contamination protection during all of the spacecraft INT and launch and early operations. And that was the door opening in our TVAC at the instrument level. And then you can see it flops all the way to the back so that we have a clear 180-degree field of view out of the front, so we don't get any glints off of any door mechanisms. And then, as I said, it has the common paraffin wax pin puller that is common to both NIFI and WIFI. So hopefully it'll do that again in space real soon. Polarizing filter wheel. So both the WIFIs and the NIFIs have a filter wheel to provide the polarization, that is putting the P in punch. So we have, it's common to the instruments. We actually, at NRL, we built the filter wheels and the actuators for both the WIFIs and the NIFIs. And they have a polarizer that is at -60, 0 degrees, and 60 degrees linear polarization, and then a clear glass filter, which is to provide the same optical path length as the polarizers, and then a blank so that we can use that for the blank. It's just a piece of black aluminum. So for safing or to do calibration testing with the LEDs that are in the camera behind that filter wheel. And the polarizers we're using are aluminum nanowire lithograph filters. They're really pretty cool and have really a great contrast and transmission in the white light. So the punch camera, again, this is a common camera for both the WIFIs and NIFIs, and is provided by RAL. You can see the elves that made it pictured there with Nick Waltham. So it's going to be very good camera. Just some quick slides on environmental testing. So this is the environmental testing that we did at the instrument level at NRL. So we did vibration testing in 3 axes. We did thermal vacuum testing, over you can see it in the thermal chamber, to simulate the temperatures on orbit in vacuum and operate the instrument in that environment. And then we also did, before we did the thermal vac and the vibration testing, we did our optical testing in the Scotch test facility. You can see here, and you can see the instrument in the Scotch facility. Wi-Fi also did their optical testing in this facility. And then we delivered to San Antonio. So we handed it over to SWRI with some of the team pictured here. I am one of those people, the shortest one, if you can believe it. So this is us delivering to San Antonio for integration onto the spacecraft. And here is the NIFI integrated onto the spacecraft at San Antonio and some door testing. And then, of course, it went through all the environmental testing all over again at the spacecraft level with San Antonio and with SWRI. So, and then here are some more recent photos. I've been told that SWRI has been taking very good care of the instrument. It is very clean. You can see the cool black light photos and the white light inspection photos. And the instrument looks clean and ready to go for launch. So NIFI meets all of its driving requirements and science objectives. NIFI was successfully delivered to the PUNCH mission and spacecraft and has gone through integration and environmental testing. So NIFI is ready for launch. So go NIFI, go PUNCH. Turned it over.
Thank you so much, Robin. All right, now we're going to go on to, that was the near field imager, NIFI, and we will go on to the wide field imager, or WFI. It'll be Glenn Laurent. Let me just pull that up. Yeah, I'll try. There you go. I think that's it. Here you go, Glenn.
Thank you, Sarah. All right, my name is Glenn Laurent. I am the WFI instrument lead of the three instruments on PUNCH. And I am proud to say that as of just a couple days ago, I've been monitoring the images coming out of all four instruments. They are all working as designed, so I'm happy to say that. And so I will be focusing on our performance on delivery, as well as observatory INT, and then showing some pretty images. As Craig and Robin mentioned, the three WFI instruments complement NIFI by providing or acting as a single unified instrument. WFI observing from 5 to 45 degrees from the sun, and both WFI and NIFI are polarizing instruments through the use of a rotating filter wheel. The three WFIs are spaced out at 120 degrees, observing again from 5 to 45 degrees. Full coverage every 32 minutes, individual sets of observations at 4 minutes. And then as you can see in the video, there's 2 sets of images, and then we roll 30 degrees every 8 minutes. So over a period of 96 minutes, all three WFIs will observe all areas of the sky. So this is a cutaway of the WFI instrument showing the baffle design. The baffle is designed to attenuate to a high degree solar light, as well as earth shine and lunar light. Light then goes through a polarizing filter wheel, goes through a set of custom optics, and then comes to a focus on a CCD camera. There's a one-shot door with a hop actuated paraffin pin puller. This shows the WFI 3 instrument just at delivery. In its final form through final inspection, wrapped up in its MLI. And all three instruments have slightly different looks. So I can tell you which WFI is WFI by looking at it, but they're all pretty much the same, which is a good thing. All right, WFI block diagram, which I've shown before and Robin's shown multiple times as well. Just highlighting again, this is a single virtual instrument, so there's a number of common elements, including the polarizing filter wheel, the camera housing, the back-end electronics on the cameras, the hop pin puller, and thermal elements as well. So as far as high-level driving requirements, we meet all of these with considerable margin, including angular resolution and sensitivity. So the Wi-Fi instrument is synchronized to NIFI as far as CONOPS. We have 2 sets of observations every 8 minutes going into each of the 3 polarizers, and then after which we roll 30 degrees. All 3 Wi-Fis went through intense rounds of comprehensive performance testing, including camera focus at multiple levels during INT, environmental testing with Vibe and TVAC and T-balance. The Wi-Fi 1 instrument was brought to NRL for stray light testing at the Scotch facility in order to validate the stray light design. All 3 instruments were delivered last year, and additional optical testing was performed and functional testing was performed at the observatory level as well, which I'll get into. On a lower level requirements, all requirements have been verified and closed. No major surprises here, a couple of waivers, but nothing that drives anything. So all of those have been closed. First stage of environmental testing is, of course, vibration testing. Here is Wi-Fi 3 mounted on the in-house in-house vibration facility in San Antonio. All 3 axes vibrated to modified GEVS levels and meet requirements. Moving on to TVAC, here is Wi-Fi 3 in the chamber where we simulate our space environment, both hot and cold, multiple 8 cycles, as well as a long soak for thermal balance, both in the horizontal and vertical configurations. And then during TVAC, we open up the door, and that was successful as well. I will say we did lose our lead vacuum technician, Roy Graham, last year. He was instrumental to testing. He was an excellent vac tech and an even better person and a good friend of mine. So. Again, multiple times, we tested the Wi-Fi optical focus throughout integration and test. We look at an artificial star across our entire field of view, measure the point spread function, which meets the requirements of 3 arc minutes over the 20-degree field of 20 degree, plus or minus 20 degrees field of view. So as Craig mentioned, we worked with the SOC, Marcus Hughes, being able to, while each of the focus spots of the raw images do meet our requirements, Marcus is able to improve those things even further by correcting for coma, by doing something called point source regularization. On the left, on the 2 images on the right, the left is the raw image that shows some coma, which is inherent to the optics. And then after correction, we're effectively Nyquist limited. So this allows us to combine images taken at different times and multiple spacecraft and create mosaics, and again, acting as a single virtual instrument. So hats off to Marcus's team. During TVAC, we also took cold images of point sources and corrected for, working again with Marcus on de-streaking, which is inherent to the pseudo-frame transfer design of the camera. So we're able to, these are very, very stretched images that you're seeing here. So even at very low levels, we do see this streaking, but that goes away after processing. So again, focus was tested at many times over all levels of INT, from pre-environmentals, instrument, post-environmentals, post-Scotch testing, post-observatory integration, and then post-observatory environmental testing. We see the focus is stable and consistent with just point-to-point noise on how we adjust our sources. So we're not seeing any trends, which is good. So in addition to focus, we measure the vignetting function of Wi-Fi by looking at a flat screen. This allows us to measure the vignetting both at the inner field of view, which is the blacked out part on the left side of the field, which is just basically just over the solar vane horizon of the instrument, and as well as the vignetting on the corners of the field of view due to our optical lens assembly. So we've modeled that vignetting function so that for pixel by pixel, we're able to have our baseline vignetting function that we implement for our processing. That will be refined as we observe stars as they drift over our field of view over a period of several weeks. But at least we have a strong baseline to start from. So in addition to vignetting, we also have an onboard calibration lamp where we have 2 LEDs. And by pulsing these multiple different times, we're allowed to, we're able to determine a within pixel calibration curve for each pixel, and basically stitching together a composite flat field. Let's see, left image just shows our obscured pixels. While we operate in a clean room environment, there are some obscured pixels, which are either bad pixels or some minute amounts of dust. That's well within our requirements. And then on the right side shows our polarizing filter wheel calibrations post-delivery from NRL. So similar to the trending of focus, we look at our calibration lamps over a period of time, and all instruments, all the 3 WIFIs and NIFI aren't showing any trends, which is good, and that allows us to track to make sure we don't have any additional contamination on the CCD. So during observatory, for end-to-end testing, including the radio and the reaction wheels, we look at our bias levels and our read noise. Those are stable and meet our requirements. So we're not seeing any additional noise when the radio is on versus off. So that's an important thing to do. Same goes for the dark noise testing. The small trends here are just consistent with small temperature fluctuations, but are all meet our requirements. So all 3 WIFIs were delivered to the observatory. That's the typo, that should be 2024. This just shows some images of that. And then post-delivery, again, we did a full suite of testing, including read noise, LEDs, filter wheel, door open tests, as well as optical focus testing. And then after observatory integration, now we're here at Vandenberg. So I think Craig may have shown some of these images, but I'll go through them again. On the left shows all 4 of the spacecraft, NIFI, WIFI 2, WIFI 3, and WIFI 1 in the far field there. And then on the right side just shows us at delivery orienting the WIFIs vertically for our door testing. So again, at Vandenberg, we perform a abridged set of tests. We can't really do optical testing due to schedule constraints and laboratory constraints, since we have to play nicely with Spherex. But again, read noise, bias, LEDs, polarizing filter wheel, and a door open test. Just another image showing the door open test here. The testing of the motorized light band, which again is the interface between us and the launch vehicle ESPA ring. And then Craig showed that, but I like this UV inspection image of the solar panels there. So this is a short little video showing the deploying of the solar array. And it works. So looking forward on commissioning and calibration, as Craig mentioned, there are effectively 3 stages, although they do overlap, of both spacecraft commissioning, instrument commissioning, and constellation commissioning each 30 days. This plan has been well defined with our observing scripts written, which identifies exactly how do we want to point, how are we going to command the polarizing filter wheel, what type of image types are we doing, what exposure times, and so on and so forth. So that has been well defined, and I've been working with the mock on scripting those observations. So there's a number of things we can do during spacecraft commissioning with the door closed. And that's looking at, we fire up the cameras, and that will happen just a few days after launch. So we'll be back at the mock for that. We can do thermal verification, again, using our onboard calibration lamps, look at our bias, our darks, LED imaging, and linearity, and then verifying the polarizing filter wheel as far as the motion and then the resolver repeatability. So initial tests during for the open door activities is, okay, we look at the star field. Are we pointed where we expect to be? Are we pointed where we expect to be pointed? If not, we can make a correction for our ADCS pointing. Look at our point spread function performance, compare that to what we found in the lab, and refine that PSF mapping and the point source regularization. Measure our plate scale, field of view, and distortion. And the vignetting function is important, and that's part of the photometric performance. So over a period of a couple of weeks, let's look at a star in one part of the field of view, watch as it drifts to the side, and then now you know your vignetting function. Similarly, multiple images of the star field allow you to verify the polarizer performance. This is just Metis images there, but gives you the general idea. Look at a star or look at a polarized source at multiple different filter wheel positions, and that allows you to verify your filter wheel. So we've just talked about our individual instruments. Again, this is effectively a single virtual instrument. So individually, we look at our point spread function, field of view, photometry, and polarimetry. But constellation calibration requires understanding these items very precisely across different spacecraft. So this is handled at the SOC level, and it effectively uses the exact science data that's used to calibrate the individual instruments. You just need to pay good attention to the cross calibration between the instruments, looking at the overlap from multiple instruments in the same field of view, as well as the overlap between WIFI and NIFI. So again, the point source regularization will be important in order to combine images to make a mosaic. As well as distortion, making sure we can combine different WIFI instruments properly together. And that's it. Go punch. This the first image on the left there is our first light image in the laboratory of WIFI 1. And then the image on the right was an image taken by me of the engineering instrument at McDonald Observatory with the Milky Way in the background. So yeah, go punch.
All right, thank you guys so much. And can we have our three speakers to come up here on this table? And can we get the lavaliers for them to use? So come on up, Glenn and Robin and Craig.
Can we introduce Ryan?
We can't. We'll start with that.
So Subi couldn't be here today because he's down at Astrotech managing the final integration. He's our project manager, Ronnie Killo. Thank you, Lika, for stepping up and introducing our fine support from NASA, without which we really couldn't have been here. And apologize for not bringing along at the beginning. I got a little discombobulated with the AV. But Ronnie is attached to the Zoom and we're ready.
I think, can you speak, Ronnie?
Yes, can you hear me? Hello, can you hear me?
Try that again. All right, try again, Ronnie.
All right, hi, can you hear me?
Yes, we can. Make him big. I'm going to try to make your picture big. So how do I pin him?
Oh.
Spotlight for everyone. I hope that works. Okay, we see you and we hear you. Thank you. Oh, wait, hang on. Stop share. Now, I believe we can see him on the Zoom, right? Okay.
You're live on the screen right now.
Perfect. Go ahead.
Okay. All right, great. Well, good morning to everybody. I'm Ronnie Killo. I'm the Punch project manager. I'm on site out here at Vandenberg. Actually, you can see, don't take any pictures, please. One of the fairings, actually, of the Falcon 9 in the background behind me. As some of you know, I've endeavored to join you at the last 2 science team meetings. I've had life events that have prevented me from doing so. One about a year and a half ago, and then, of course, this past June, I had a wonderful granddaughter born very early. And so I was actually in Boulder for the science team meeting and had to depart rather quickly. And so unfortunately was unable to join you once again. And now here we are at Vandenberg, and had hoped to join you there this morning. But with the shifting schedule, as always happens with launch site integration, I wound up having to be here at Vandenberg and not able to join you there at Cal Poly. But anyway, I just wanted to greet all of you. Thank you for your support of Punch. Obviously, we are doing this for all of you, the science community, and so we have endeavored to build 4 great spacecraft, and I think we've achieved that. As Craig said in his remarks this morning, it's certainly been a winding journey and a lot of challenges that we've had to overcome along the way. Not the least of which was COVID very early in our mission, of course, as everyone had to deal with, and then being paired with SphereX. As we're a ride share to SphereX, as you're aware of. And by the way, that relationship has been fantastic. SphereX has been a great partner for us to launch with, both because we're all going to the same orbit. We have the same cleanliness requirements, so we're very compatible from that perspective, but we've also been very compatible with our cultures together, and they've been very kind to us as a ride share to them. So I wanted to publicly thank the SphereX team and let you know that they've really treated Punch very well. So again, we're doing this for all of you. We've got 4 great spacecraft. You heard about the 2 instruments from Robin and Glenn this morning. As Robin indicated, we've endeavored to take very good care of all the instruments. We've had regular cleanliness inspections, and those have come out just outstanding. We've kept those instruments very, very clean. And we are now stacked and ready to, perhaps as soon as today, be encapsulated into the fairing, the rocket fairing, roll out to the integration facility where we'll be mated to the rocket. Could happen as soon as tomorrow. Again, these launch integration schedules are very dynamic, as you can imagine, but we're getting very close now to launch, currently scheduled for Friday. We'll keep everyone posted if there's any changes to that schedule, but we're very excited to finally be here. We've got 4 spacecraft that are working very well. And as Glenn said, the images continue to look great as we do some limited functionals, of course, out here at the launch site. But anyway, again, thank you for all of your interest in Punch, and we hope to be launching soon and get some great data for you guys to chew on very soon. So thank you very much.
Right, thank you, Ronnie.
You know, one of the things that we are seeing is traces of solar variability. It's one of the examples I'm just taking. So my question would be, would it be possible to freeze one of the wikis if there is one structure that we are interested in, just freeze it at one position for a while until I think I got yours.
Yeah, the issue there is, we want to make sure that the Earth doesn't enter the field of view there, so. We have our condoms where we roll every 30 degrees every 8 minutes.
Okay.
Just to follow up, yes, we will never stop rolling. The whole idea is that we calibrate these as best as humanly possible, so that it doesn't matter where on the detector I get future falls. And we worked very hard to make that a reality.
So you said 30 minutes, you are in the same angular position for
30
30
minutes.
minutes?
So they overlap, so Wiki 1 will overlap Wiki 2 within 32 minutes. So 96 minutes for an entire orbit, 32 minutes for overlap to overlap.
But within that 30 minutes, they get exposure timing things.
That is,
No. No, we don't do that.
no. Certainly during commissioning, we optimize our observing exposure times based on our signal to noise, and then after that, it's fixed.
So Lou, remember, this is just a SMEX mission, not Parker Solar Group. And what they're doing still is extraordinary, I think, and we should all be thinking of how to make our missions with maximum science benefit with the least amount of, resources that we put in. But I just want to sort of at least bring to your notice about the requirement for open sign. And I'm not going to say whether it was there or not. You guys know it very well. But one of the things to remember, don't try to get too caught up in that, because this community has practiced open signs as far as I can remember from the starting of trace days. So that has been a self-imposed constraint for this community.
No, I agree. And big role of science, we want just to figure out if there are requirements, we have to answer that. But for Mika, you are NASA. And I remember in the early, NASA is always overachieving. So that's funny. I remember the early days of Parker Solar Probe. I was asking for more and more from the engineering team. And at a certain point, they were frustrated. And one of them told me, we are meeting the requirements. My answer was, if we are only meeting the requirements, we are failing. That's actually for PUNCH6.
Thank you for your presentations and congratulations. It was amazing to see those video pictures. So my question is, what is the first slide? How it's coordinated between the instruments, and when will we see the first image from the punch?
So again, 3 phases of commissioning. First data will come in within, as far as first contact, within 14 minutes or 45 minutes. This is not science data, of course. And then cameras are turned on, assuming everything goes well, within a few days, as far as the cameras themselves with the door closed. And then sometime during the second part of the commissioning phase, meaning the second 30 days, the door opens. We start receiving calibration data. And then during the third phase of commissioning, we effectively perform at least our initial nominal science observations and make sure everything's working there. I don't know if we're streaming those, we're sharing the calibration data or not. Greg, you can answer that.
I think we're not pushing them out, but if people want them, they can have them. It's not clear, but we may end up with a picture of your house.
I've added that as part of the commissioning phase. We will roll Wi-Fi, take an image of both Boulder, Colorado, as well as San Antonio. So
we're looking for bodies of water to calibrate the polarization.
that's
Rob mentioned that there are things in common between the NIFI and the WIFIs. Like I think the cameras are in common. Do y'all think that it was an advantage to have some things in common? Did it make the spacecraft integration easier or more difficult? Because these small missions are probably a lot of the future of the field. So I was interested in that.
Well, I can't speak to the spacecraft integration. I can speak to the instrument integration being the one different spacecraft. Things are always common until they're not. So I think the camera being the same, we did have to do some engineering and some coordination. It takes more coordination between the teams when you have components, because you have to make sure that you're meeting everybody's requirements, and then we had to make some modifications to how we were taking to the NIFIs versus the NIFIs, because they're just physically different. So there's a lot more overhead, but I think it's really going to pay off when we get the data down and we have the same camera that's operating all 4 of these. So maybe a little bit more engineering on front end, but hopefully that's going to pay off soon.
Certainly from the SOC perspective, it's very beneficial to have a unified pipeline looking at the same cameras, the same LED calibration images, same filter wheels. So it's a lot more smooth.
Everyone, I'm Rebecca, the outreach lead for Muse. And on behalf of the Muse PI, I'd like to contribute to Craig. He sends his deep congratulations to the entire Punch team. I'm curious about your water supply on board for electrolyzing and propulsion. Muse and its legacy instrument IRIS doesn't have a propulsion system, and a couple months ago we were faced with our first real fear of impact without any ability to adjust course. So will you be able to adjust course if there is a threat of impact?
Absolutely, we will. We have something like, I forget the exact number, and Ronnie may want to correct, but something like 1 liter of water on board, and that's multiple, it's a factor of multiple times what we need for orbital trim during the prime mission.
So going back to the stress that you placed on the commonality of designs, why is the filter wheel behind the lens assembly on NIFI and out in front on WIFI?
For the NIF, in the end, it shouldn't make a difference for the science and the data. I can say that for the NIFIs, that is where we've always placed it, and also we have a lot more light coming into our field of view as opposed to the WIFIs, since we're looking closer to the sun and falls off by worse magnitude in our field of view. So having the light rays coming in as parallel as possible at the end of our, very close to our focal plane was more advantageous for our optical design. Sorry, my optical engineer said the same. So shake, not shaking his head no. So.
I'll speak to the WIFI side, which is we put the polarizer in front of WIFI because it's a much faster beam than the traditional coronagraph or even the NIFI. And so we were worried about contamination across the field or inability to calibrate across the field for the exact polarization angle. It turned out that was for naught, because the WIFI field of view is so wide, we actually have to worry about perspective projection of the polarizer itself on the celestial sphere. Rajesh Patel has done a tremendous amount of work on that. Something he calls the IMAX effect. You'll see in the SOC documentation.
I was kind of curious to hear about the fact that the NIFI and the 3 WIFI CONOPS were so rigidly synchronized with one another down to the second, it looks like. I'm just curious how that's done. Is it all uplink, downlink, or are there like synchronized clocks aboard all 4 spacecraft?
Our original CONOPS was to jam time, and it turns out we can jam time to within a second. So we synchronize the clocks on board and we uplink and passes. But then one of the engineers pointed out that GPS is actually not that hard to implement, so we did. But we normally operate off GPS, which just gives us rock solid timing. But should that fail, we can jam time. That works on.
This is Wade Yu from Lockheed Martin Astrophysics Lab. I have 3 questions. First question is, after commissioning, would you do periodic calibration drones that would cause some interruption to your data flow? And how much would that be your data budget?
We do have periodic calibration times. I don't remember where they are in the columns, how often they are, but they're a negligible fraction of our observed time. Robin mentions they are during the eclipses, so we're not losing any important data.
Great. Second question is, do you have flexibility to adjust your observing sequence, for example, exposure time, cadence, for some particular or special operations like coordination with other instruments? I'm asking because some objects like sun grazing comets, they could be very faint, and would you be able to increase your exposure time to allow capturing those faint objects?
We have no plans on doing that.
In the normal CONOPS, our shutter is open 60% of the time. So we're getting all the photons we can get all the time. So the plan is to not change our mode of operation at all. We're open to that after the prime mission, but not.
Third question is probably more a question to NASA. Would there be any gas investigator programs after the prime mission for proposal opportunities, for example?
I'm looking over to see if Leak is going to answer that. The program executive is there as well. I would very much like to see a guest investigator program. It's not clear to me whether that can happen yet, but other people are working on it.
Thank you.
I am very sorry. I'm doing a little bit of my day job and was completely engrossed in this work of the question.
Guest investigator.
Well, I think that is a question better asked of our research director.
We do indeed plan. I'm not sure it will be a dedicated guest investigator for PUNCH, but we do appreciate that. I think this year we are launching 6 missions, of which PUNCH is one. So we are well aware that we need to add some more to enhance the guest investigator program to accommodate all these new missions. So yeah, we are aware.
So I've heard it a couple of times that PUNCH has the most advanced SOC of any Explorer mission. There's a bunch of work that you guys had to do like distortion reduction to be able to stitch the images together well and things like that. So I was just wondering if any of that stuff is going to be open also, or if you think that that's going to be useful for future small missions. We're going to be doing a bunch of this moving forward.
Absolutely. You're going to hear all about that from the SOC talk after the break. And yes, all that stuff is good.
You mentioned something about the associated investigator, which just follows from the guest. Is it the same? Is it on the same lines?
So we organized an associate investigator program, which I intend to keep through phase C, in which when younger scientists get involved and start engaging with the mission, they can be recommended by working group leads to become a formal part of the team, even though we don't have money for it. And so that's the associate investigator program. It's turned out to be very successful because it recognizes folks who are really doing great things for the mission and allows us to give them an on-ramp to later stages.
So it's going to come back at some point.
Yes.
talk a little bit about how do you plan to organize the work of the science team starting from phase Z? In regular meetings, calls, working groups, and so on.
Thank you, Elena. Yeah, so we have a wonderful science team. And if you go to our webpage, the main PUNCH webpage, there is, and you look in the drop-down menu for science, you'll see science working groups. And the science working groups are made up of co-Is, PUNCH co-Is, who are essentially, their goal is to deliver on the promise, the science promise for PUNCH, a lot of which is to basically create products, tools, and some initial results out to the community to make it accessible to a much broader community. We've already started reaching out through these workshops and through what we call topical working groups, because the working groups are sort of, we're closing on what we have to do for NASA as part of our contract with NASA. But the topical groups are trying to branch out to the community on certain subjects. And the ones that are there now, and you can find these on our webpage, are the flow tracking, and Rafael Ate is going to tell you more about that, and the CME challenge to try to take synthetic data and see if you can predict where a CME came from. So I encourage you to take a look at the website for those. But this is just the beginning, because of course now we're going to get the PUNCH data, and the fun really begins. So you're going to hear about how the SOC is going to get out the level 3 data. You're going to hear about what the working groups are planning to do and to provide to the community. Beyond that, we will continue to have these annual meetings. We will have quarterly working science team meetings, which we will probably open up for people who are interested to join. So you can just basically ask me or any of the other working group leads if you want to kind of plug in that way. We'll always be having these annual meetings. Let's see what else. We're going to have we have a topical issue of solar physics, which is just coming to fruition with a lot of the information about the models, the tools, the observations, the techniques of PUNCH. And of course, we'll have first light science papers coming out. What am I forgetting, Craig?
Talk to people.
We're going to be talking to people. So essentially, we are open data, open science. We really want to interact with you. We have certain things we want to get out right away so that we can give you those maps of flows and you can do whatever science you want with them. So we can start doing some polarization analysis and give you tools to do the kind of analysis you want to do in 3D. There's also interesting synergies, and the way we organized this meeting today and tomorrow was to have a mission synergy panel this afternoon and a model synergy tomorrow. So there's a lot of things which are not part of our mainline mission, but are going to come out of PUNCH because these data are unprecedented. We're going to see things that have never been seen before. So we cannot predict in advance everything that will happen scientifically. So we're very, very open to anything anybody wants to do with the data. And the on-ramp for that is our webpage, our SOC tools that they're going to give you, myself, and the working group leads, and Craig. We're all very, very eager to work with you. So hopefully that answers the question.
I'll jump in a little bit on
I'll jump in a little bit on our organization, which is, I owe a fraction of my career to people like Russ Howard, who's here in the room. I spent a lot of my early career being a thorn in the side of existing PIs. Why isn't this data better? Why can't we do better? Give me the raw data. I want to fix it. And the tolerance and willing to work with, pretty irascible young Craig got us here today, right? And so we're trying to push that forward by engaging with young folks. If you think we're screwing up, excuse my French, tell us and show us what we're doing wrong. We'd love to see that. So, we've worked very hard to make sure that raw data are available as well as process data and all of the tools so that you can do better. We love it if you do better than we can.
From Boulder. Sarah already replied some of the questions. So my question is, what's the typical data product, for example, after calibrated level 1 include photo brightness, PB, and polarization. Even though from ASCO and stereo, they all have this important calibration for background subtraction. So even though the background changing with time, so also has separation of F corner from K corner in order to get the quantitative density or 3D structure in motion. Can you introduce briefly?
So, that is a great question about how do we process the data and what are the different things that we'll find in each data product. It's an entire talk, and fortunately, we have one queued up right after the break. So I'm going to defer that, and after Marcus speaks and Chris talks, then re-ask the question if you haven't been satisfied. Russ will be talking about this.
And the question is, why not for NASA? Tomorrow, I believe there is a lunar launch from the Cape. Is there any possibility that launch will impact our launch? Because I know NASA doesn't like to have two scientific instruments going at the same time.
So, as you might know, the lunar launch has a specific window, so it will take precedent over the punch launch. So if for some reason that one gets delayed and impacts the punch launch date, then punch will actually step outside of the window. So that answers your question.
All right, then back to Sarah, who will tell us where to go get coffee.